Hello everyone, this is Irin and welcome to today's video which is about the elastic constants study of materials using Materials Studio, and this video is divided into two parts. In the introduction to elastic constants, where I will give you a brief idea on elastic constants and its importance, as well as how CASTEP code actually simulates elastic constants. And the second one is how you can use CASTEP code tool for the elastic constant calculations of a crystalline material. The introduction to elastic constants. First, begin with why is it important to study elastic constant of a material? Well, studying elastic properties of solid materials holds interest in both basic research and technology. They allow you to explore many physical properties of a material or system. For example, whereas the material has mechanical stability or not, possesses brittleness or ductility, the presence or absence of phase transition, the strength, acoustic behavior, machinability, thermophysical properties, anisotropic or isotropic nature, and many more. And in order to get more idea, you can study some of my recent works, since all of them are summarized there. And for your convenience, my Google Scholar and ResearchGate profiles links are in the description. Well, basically elastic constants are relation between stress and strain, and it do or don't obey Hooke's law of elasticity based on the order of elastic constants, which we will see later. And here I am presuming that you all are familiar with the Hooke's law of elasticity. The generalized Hooke's law defines the elastic constants as ratio of stress to strain, where the sigma, epsilon and the uppercase C defines the stress, strain and elastic constants respectively. There are various orders of elastic constants, namely the second order, third order, fourth order and so on, where the indices I, j, k, l represents the Cartesian coordinates in 3 dimensions. The second order elastic constants based on theory of linear elasticity, where infinitesimal deformation strains are assumed and describes linear response of a crystal with stress, whereas the third, fourth and the higher orders elastic constants based on the theory of nonlinear elasticity, which describe the nonlinear response of a crystal with stress, and they are used to explain anharmonic phenomena in solids. Here I will focus on the second order elastic constants, since CASTEP code calculates the second order elastic constants using the first principles method. The second order elastic constants explains the linear elastic stress strain response and obey Hooke's law of elasticity. The CASTEP calculates elastic constants from initially applied finite strain or stress and then optimize the structure, and finally calculates the stress or strain respectively. The actual calculation of elastic constants in CASTEP is performed at the analysis part, and the total number of elastic constants is the same for all crystal systems with similar dimensions, for instance 2 into 1 for second order in 3 dimensions, and it also depends on both the order of the elastic constants and dimensions. And also the number of independent elastic constants, that is the minimum number of elastic constants required to explain a system completely, is different for different crystal symmetries, and we can get the rest of the elastic constants out of these independent elastic constants. And the number of independent elastic constants for different crystal systems are summarized here. And the mechanical stability criteria. Every crystal structure has different stability criteria for assuring their mechanical stability, and all of them are summarized here. Here you can see the stability criteria with their corresponding crystal structure like cubic, hexagonal and so on. Now moving to the simulation part. Here I will show you the simulation and analysis of elastic constants of orthorhombic molybdenum carbide. And here I have opened the materials studio file for the compound, and the elastic constants study is also divided into two parts, the run and analysis. And in the run part, here I will show you the simplest way of calculating the elastic constants of a material. And in order to make some space, I am removing the properties explorer from here. Here, this is the geometry optimized folder for the compound, and if you don't know how to build and optimize a structure, you can search on YouTube how to build and optimize crystal structure of a compound. Now back to the topic. Open the geometry optimized folder by clicking on this plus sign. Now open the 3D atomistic figure from the geometry optimized folder by double clicking on it. Here I am maximizing the window. Now open the 3D atomistic calculation from the geometry optimized folder in order to open the CASTEP calculation dialog by double clicking on it. Now from the setup tab, you can select the type of task you want to perform. Since here we want to simulate the elastic constants for the material, so change the geometry optimization task to elastic constants from the drop down list. And leave all the other parameters that you choose for geometry optimized calculation untouched. And now click on run to start the calculation. Here in the job explorer, you can see that the simulation has been started. Generally, elastic constants run demand more time as compared to most of the other properties. It also depends on the symmetry of the structure of the crystal and make some constants equal and some are zero. Therefore, the number of independent elastic constants varies from structure to structure, as I mentioned earlier. Now the calculation has been completed successfully. Click on OK and remove the CASTEP calculation dialog. And now the second step is analysis. The actual calculation of elastic constants is performed at the analysis stage based on initial strain and calculated stress. Now open the 3D atomistic file. It is already opened. Now go to the CASTEP tools in the toolbar. Select analysis and it will open the CASTEP analysis dialog. Now select the elastic constants. Click on calculation. Now remove the dialog. And this will generate a new file in the name of 3D atomistic elastic constants. And this file contains many parameters such as all the independent elastic constants. Like here, you will find all the independent elastic constant for the system and the elastic stiffness constant, elastic compliance constants, and different moduli like Buck modulus, shear modulus, Young modulus, and many more. And you can calculate many other parameters out of these, as I mentioned in the beginning of the video. So go through the file, and thanks for watching.